Alright guys, welcome to our channel Code with Sunny, and in this video I will be talking about the problems of July Easy 2021 of Hackerearth. Okay, so the contest was very much easy and not that is easy is a relative term. We can't say that some problem is easy. It will totally depends on the person that is solving that problem, right? And the coding skills that the person he or she should have. Okay, so talking about the first problem. Okay, so let's move further to discuss this problem. Okay, so in this problem, actually the problem requires the concept of some bit manipulation and the concept of two pointers. I think the many people have solved this problem using the help of segment trees, sparse table, and all that Fenwick tree also, I don't know. But this problem can be easily solved without the help of data structures. So we have to store the prerequisites of the prerequisite values of we have to store the positions where the bit set bit is occurring. I will tell all that stuff for now. Let's understand this problem and then we'll together move further to the best solution for this problem, right? Okay, so we have been given an array A of length n and an integer x. So there will be an array of array consisting of values starting from 0 and it goes up to 10 power 9, and there will be an integer x that will be given to us. X is also varying up to this range, and you need to find all the subarrays of minimum length with bitwise or greater than or equal to x. Okay, now the concept is like very much similar. You need to first find it out if what is the minimum length of subarray whose bitwise or is greater than equal to x. In other words, if you try to find out the all the subarrays whose bitwise or is greater than or equal to x, for all those subarrays you need to just find out the minimum length subarray. Okay, let's say the minimum length is some value y, then you need to find all the subarrays whose bitwise or is greater than equal to x and its length is just coinciding with the value of y that we have found now. Okay, I think the problem statement is now clear, and let's discuss over the input format. Test cases will be given and an x and then n space separated integers denoting the elements of the array. Now note that for each test case we need to first print out the count of such subarrays whose bitwise or is greater than equal to x, and that like subarray has the minimum length, and next C line should be printing all the subarrays in a sorted form. Okay, so how we are going to do that? Okay, as I have already said, the concept is very much similar. Of two pointers I am going to use, and then we will together find out the total subarrays for that. Okay, so let's move further to understand this problem in a little bit detailed manner. Okay, so as I've already said, I am going to use the concept of two pointers. Why two pointers? Because the approach that is, as I'm going to explain that the reason behind the use of two pointers. Okay, so suppose we have some elements of the array like 1 2 3 4 5, and let's say x is 7. Okay, I'm just picking this example from the sample input. I think yes, x is 7. Now just consider one thing, that you need to find the length of the smallest subarray with bitwise or is going to be like greater than equal to the value of x. Okay, now consider one thing, that if you, let's say, there will be two pointers like j and I. Initially j is over here and I is also over here. Okay, now consider the sequence of steps. Like now you can see I am just including the very first element. If I will include the very first element, what is the bitwise or till now? Bitwise or till now is 1, and 1 is like not greater than equal to 7. So we need to include more elements. So I will include these two elements. If you will include these two elements, you can see the bitwise or of 1 and 2. You can see it will come about this one, 3. So bitwise or is coming about 3, and still it is not greater than or equal to 7. So we need to include more elements. So I'm going to do this one. You can see on including this first 3 elements, still the bitwise or is not greater than equal to 7. So I need to include more elements. So I will include this one. So after including 1, 2, 3, 4, you can see the bitwise or is coming about, let's say we will do that. This is for 1 and this is for 2 and this is for 3 and this is for 4. What is the bitwise or of these 4 elements? You can see it is 7 easily. all the three places will be filled with set bit equal to 1. Now you can see the bitwise OR is coming about 7, and it is actually greater than or equal to 7. So it means that here we have find the subarray of length 4. Now the approach is like very much simpler. You can see the J is now over here and I is over here. Okay, so can we get the can we compress this subarray to to length lesser that is okay, so let me explain in some different words. So now we have a subarray of length 4. Now we will try to compress this subarray of length lesser than the current length such that the bitwise OR is still greater than equal to 7. Okay, you can easily see if I will move J to the next step, that is now I am considering the subarray starting from only this 2 3 4. That is now I find the subarray of length 4 from 1 to 3 4. Now I will try to compress this that is move the pointer J to the next position. I will try to compress this subarray till the bitwise OR is going to be like greater than or equal to x, where x is now 7. You can see if I will eliminate this one, that is move the J pointer to the next position, you can see my elements are 2 3 and 4, and if you take the bitwise OR of this 2 3 4, you can still see that it is coming about 7, and which is like greater than or equal to x. It means that we can that is eliminating one is like useful, because we are getting a subarray of length 7, not sorry for the length 7, subarray of bit having the bitwise OR exactly equal to 7, and still it has a length equal to 3, which is lesser than the length equal to 4 that we are previously getting. Okay, so eliminating one is useful. Now can we eliminate more elements? Like can we increase my J pointer to the next step? If you will consider this, that is eliminating this 2, the bitwise value of 3 is like I think 1 1 and 4 is like 1 0 0. You can say still the bitwise OR is coming about 7. It means that eliminating 2 is also valid. Okay, so if I'm getting 3 and 4, now you can see the bitwise OR is still greater than equal to 7. Now we will have a minimum length of 2. Okay, now we will try to check if eliminating 3 is going to have, that is if I will try to eliminate 3, subarray starting from J to I, that is the only 4 element, that is the only element 4, you can see the bitwise OR is now going to be strictly less than x, and it is not valid. Okay, so I will try to move this pointer I pointer to the next position. You can see now we will have the elements like 3 4 and 5. So what is the bitwise OR of this 3 4 5? You can see bitwise OR of 3 4 5 is coming about 7. I think 7, right? So I will put a 5 over here. You can see the bitwise OR is coming out 7. It means that still we are getting the length equal to 3, but we have already found the minimum length as 2. So we will try to again compress this J pointer to the next pointer. You can see it is coming about, if my new J pointer will be over here and my I pointer will be over here. So I will find out the bitwise OR of 4 and 5. You can see 4 is this, 5 is this. And you can see the bitwise OR is coming about 5, and it is like not greater than or equal to 7, so it is not valid. So we have already find the minimum length subarray whose bitwise OR is greater than equal to x, and it is the subarray starting from the index equal to 2 and ending at index equal to 3, that is subarray with 3 and 4 value. So this is the minimum length. Okay, so my length, minimum length is coming about 2. Now if we have get the minimum length, we need to just find it out what are all those subarrays. Okay, what are the total subarrays whose minimum length is coming about 2 and its bitwise OR is like greater than equal to. We need to find all those subarrays. Okay, now the approach is like very much simpler. Whenever you are getting that minimum length, that is my current length of subarray exactly coinciding with the minimum length, you need to just push up the coordinates of J and I, and that will be your answer. Okay, so the approach is like very much easier. So let me just move on to the code to explain. Okay, I've also forgotten one thing to explain. I think I should have to do that. Okay, so one thing that should be taken care is like, suppose we have some certain set of elements, like I'm going to do this one. Okay, so let me write down as this one. Suppose we have all these elements. Okay, I don't know the value, I'm not interested in calculating the value. I'm just writing down the binary representation of all the numbers. Okay, what is the bitwise OR of all the numbers? You can see bitwise OR of all these numbers is 1. That is, sorry, triple one. Okay, so suppose J pointer is over here and I pointer is over here. Okay, now if we try to compress this J pointer, you can see my new J pointer becomes over here. That is, I'm going to exclude this element. Okay, if I will try to exclude this element, you can see that still the bitwise OR of all these elements is still the triple one. Okay, so you need to just maintain the count of ones over all these places, like first place, second place, third place, and all these places. And what are the maximum number of places? You can see 10 power 9. So binary representation of this 10 power 9 can goes at most around 30 and 31. So for safer side, you can take the value of 32. Okay, so there will be this much amount of places. Okay, so whenever you will try to exclude this element, you will try to remove the positions of one, that is the position, that is the entry of this one over this position, right? And suppose my J pointer moves to this position, I will remove this entry of 1 from this position, and also remove this entry of 1 from this position, and also remove this entry of 1 from this position. As we all know that bitwise OR of certain set of elements, like for all, if you try to find out the bitwise OR of all these positions, all these elements, you can see if for a particular position, this one, if any of the numbers has the entry of set bit equal to 1 at this position, the bitwise OR will be 1. That is not saying the bitwise OR will be 1. The entry of set bit at this position for the bitwise OR would be always 1. And here also you can see any of the position here is 0, 1, 1. There is at least one 1, then I will say there will be the one entry of this one in the bitwise OR. Okay, you need to take care for that. And also here you can see there will be at least one 1, then you need to have entry of 1. Suppose there will be exactly, or that is all the elements at this position, that is at this position will be 0, then bitwise OR will be 0. Okay, so you need to maintain the number of ones over all these specific positions and do the two pointer approach to find out the answers. Okay, so let's move further to understand how what is actually happening over here. So you can see I've taken NNX, now this vector and the entry of this vector. Now what I've done is, like, first I've tried to find the minimum length subarray with bitwise OR greater than or equal to X. Okay, so let me just zoom it out so that it should be clearly visible. Now you can see I've iterated, my I pointer is going to iterate over this all the positions from 1 to n, and whenever I get some element I will add dp comma vi. Note that dp is a 32 size linear array, linear vector, right? So when I get this one, I will add the vi, that is I will first find it out the binary representation of this current number. You can see the add function right over here. I will just take this number and I will just iterate over this 32 times from 0 to 32, and I will first find it out if there is a set bit at the particular position of this number num, then I will increment the entry in my dp linear vector. And okay, so whenever I will get that, I will just try to increment the entry of that set bit at a particular position. Now I will just fetch the value, that is bitwise OR. This is being done by getDP function. You can see that getDP is going to just check it out. If there exists at least one entry, just increment the value, right, from 0 to 32 position. And you can see this function, this value is going to be like incrementing the power, that is 1 ll less than I is actually a 2 power I. You can write that using the help of left shift operator. If you are not aware about that, you can check the binary exponentiation video in my one of my algebra and competitive programming playlist. I've used that this term frequently to and I've also explained the significance of this term, right? And okay, now comes the important thing, the two pointer approach stuff. You can see whenever the dp is like greater than equal to x and j is less than equal to I, I'm going to try to remove this one. Okay, that is remove the entry of this position num. You can see this one, like this one, j is going to be moved to the next position. I will remove all the entry of ones in the remove function with the help of remove function. You can see if there exists a set bit, I will just decrement its entry. Okay, and increment my g. Okay, after all this stuff, it is obvious that this that is the bitwise OR is like greater than or equal to x. Now I'm going to find out the minimum length, and it would be like I minus j plus 2, and this len is going to store the minimum length. Now the all the steps are going to be very much simply the copy paste of this one. You can see what I have done is like incremented, or not saying that incremented, I've initialized j as 0 and filled dp with 0, and this pair is going to store the answer. Now again the entire same step, and you can see this one is also same, and my current length is I minus j plus 2, that is the current subarray. You can see if current length exactly coinciding with length, I will just push back the entry of the specific position, that is the length of subarray, not calling that length the starting and ending coordinates, no, ending index, starting and ending index of that subarray. You can see that it is actually a zero based indexing. Finally I'm going to print the plus 1 value, which is 1 based indexing. You can see that for each test case, in the first line print count of subarrays, then next C lines all the subarrays, and the subarrays can be defined by L and R only. That's why I pushed the only the indexes, right? Okay, so you can just optimize this entire thing. That is, first I will try to submit this code and show you out that it is working fine. You can easily see. Okay, so yes, it is all accepted. Now I will try to just remove this stuff, and we will just try to optimize my code. I'm not saying it as optimization. I will try to add something more interesting. You can see this will be stored as answer. Now what I'm going to do is like I'm just trying to find out what is my current length. Current length is I minus j plus 2, right? And if my current length is going to be like strictly less than length, it means that we have found the new subarray with minimum length whose bitwise OR is greater than equal to x. I will initialize len as, that is assign len as current length, and answer dot clear, and it means that we have found the new entries. So I will just push back j minus 1 comma I, and if there exists my exactly the length of subarray matching with my current length, I will just say I will just push back this j minus 1 and I think it's fine, totally fine, right? So let's try to submit this code and check it out whether it is working good or not. Yes, it's still good. Now this is like a good one. Okay, so if you have any doubts, do let me know in the comment section of the video. I'm trying to move further to the next of the set of problems like path queries and super jump in a grid. Okay, so let's move further to the next question, and we'll try to explain in a better possible way. Okay, so let's talk about the another problem, path queries. Okay, so this problem is actually a foolish problem because we are not going to do anything, and it can be solved with the help of basic knowledge of maths, I think. So given a rooted, this problem also is not related to the graphs. Okay, so when I first read out this problem, I just was wondering how. Okay, so I'm not going to explain that whatever I was wondering, because this problem is actually not anything related with the graphs. This math, it is actually a mathematics problem. So there will be graph G with n nodes, and every node is assigned a value, and that will be given to us. And a simple path from U to V, where V is going to be denoted by UK, is going to be beautiful if the number of pairs of nodes for every adjacent node, you can see UI and UI plus 1 for a particular path, where the first node is has the parity as odd and its adjacent node has the parity as even, and the number of pairs of this type, that is also the current node and its adjacent node, where the first node has the parity should be even and the corresponding adjacent node should have the parity odd. And let's say this first one has the count as x and second one has the count as y, then we need to ensure that x is must be equal to y, then the simple path is beautiful. And also we need to find the total number of such simple path which is beautiful. Also we will be given q queries. In a particular query we are going to change the value of a particular node to my new value and find the number of ordered pairs so that the simple path between node u and node v should be beautiful. And in the input format we will be given all that stuff. Okay, I'm not going to just talk about all this stuff, so let's directly discuss this problem. Okay, so you can see that I've already changed the parities. Like you can see that I'm not putting the values, that node values on all over here. I'm just put out the parities because the parity is going to matter over here. You can see, let's pick up some for now, whether we are not going to process any queries. You can see that I'm just picking up this path, that is u is 3 and v is 4. And can you just say that this is a simple path and it is beautiful? Yes, 3, 2, 4. You can see 3 as the parity as odd, that is the node value has the parity as odd. It is even and it is odd. You can just pick it out that what is the number of that is what is the value of x, where x is number of pairs of adjacent nodes of the type OE, and y is the count of those pairs of adjacent nodes which is of type EO. You can see OE is going to be like over here, and there is only now the next one is EO. So x is 1 and y is also 1. Here you can see that x is equal to y. So this is a simple path and it is beautiful. Okay, now let's consider some more different types of paths like of this one. So E, O, E and O and then followed by E. Suppose there exists such type of path. You can see that EO has count of 1 and EO again, that is count of EO is 2. What is the count of OE? You can see that count of OE is this one and again this one. You can see that X is equal to Y and it is 2. You can see that one thing that is noticeable over here, whenever you will try to write EO and you want X equal to Y, you must have to write OE. So it means that whatever the parity that is we are going to start with, that is we are here is starting with E, then here we are ending with E. And again you can see starting with O and ending with O. It means that we have arrived to a conclusion that for a path to be beautiful, it must start and ends with the those nodes which has the value exactly whose parity is matching. Okay, that is start node and end node has the same parity. Now there comes one more different case, like suppose we have this type of EEE, then again EO, then again E, and like of this one OE, then let's say we have something, okay, so like this one, okay. So you can see that whatever the nodes whose parity is like same for all those continuous nodes, like EEE, then here it starts with first E, then O, then ending with E. Okay, you can see that it doesn't matter whatever the same nodes that is present over here, because the count of EO and that is OE and EO is not going to be incremented during these steps. Okay, so it doesn't matter what the matter is, like start parity of start one and parity of end one. Okay, now the graph is like given to us and we have the like all the nodes of same parity. You can see that I need to just choose two nodes where whose parity is going to be same. So what I'm going to do is just find out the total number of elements which are having the even parity and total number of elements which are having the odd parity. And I need to choose two elements from the total number of elements whose parity is even. So it is going to be like even C2, and total of choosing two elements from this odd is like odd C2. So you can see that the first count is like E into E minus 1 upon 2, and plus the second one is like we need to choose two elements, so odd into odd minus 1 upon 2, right? Now you need to ensure one thing, that a particular node, that is exactly one node, that is node 3 whose parity is 0, we need to just include that one also. So there are n nodes. Okay, so I will just figure it out, like I will add the value of E to this one and I will add the value of O to this one, and E plus O is actually the total number of nodes. Okay, now you the only single node is also considered as a good simple path, which is also beautiful. So if you modify this entire term, it will becomes E into E plus 1 upon 2 plus O into O plus 1 upon 2. So if you want to answer for a particular query, you need to ensure that you have the even number, that is number of elements whose parity is even, and you need to also have the number of elements whose parity is odd. Okay, so that is the entire logic of this question. So you can see what I've done is like it is actually a foolish question. So NNQ, then array, then I will maintain the odd count and even count. You can see I've incremented this whenever I have found an element whose parity is odd, increment the odd count, otherwise even count. Now you can see I have to input the edges also, and it is of no use. That's why I have not stored this one. Now this all iteration for every query, I have taken the index I and val, and I have to change the value of a particular index. So if array of I is if array of I is odd, I need to decrement odd count, otherwise decrement even count. Now set the value of array of I as new value, and if it is odd, increment odd count, otherwise increment even count. And for a particular query, our answer is odd into odd plus 1 upon 2, even into even plus 1 upon 2 with the space, then finally print indulge after processing all queries. Okay, so let's submit this code and check it out if this is working fine or not. Yes, it is good. So if you have any doubts, do let me know in the comment section of the video. So let us move further to talk about the next set of problems like this one. Okay, so let's move. Okay, so I will be discussing first the erasing the array question because this is like very much easy and I don't know why the number of submissions is quite less. Okay, so you will be given a binary array of zeros and one, that is the array that will be consisting of only zeros and of an element. So you want to perform the following operation as many times as possible. Choose a subarray starting from the very first index which is inversion free. I'm going to also talk about this inversion free term and delete it. Finding the minimum number of operations to delete the entire array. Okay, so every time you try to start choosing a particular subarray whose starting point is like the very first index, and that subarray should be inversion free. So inversion free are there are no two indices I and j in the array A such that I less than j and ai should be greater than aj. Okay, so if you're not understanding this right now, have patience. I will discuss while explaining the question. Okay, so input format, and we need to find the minimum number of operations of the entire array. Okay, so let's move further to understand this one. So inversion, let's talk about something called inversion. Okay, so suppose we have array in the sorted form like 1, 2, 3, 4, 5. Okay, so you need to find two indices I and j such that I is less than j. So I can be over here and j can be over here and all that stuff. Okay, and the value as of this ai should be like greater than ag. Now you can see the array is in sorted form, so there will be no inversions over here. Okay, now consider the thing like I'm just introducing another element called 1 over here. Now you can see when I introduce this one, the inversion count is going to be increased. You can see that if I will try to fix j over here and I over here, you can see I less than j and ai is going to be greater than aj. Yes, there is an inversion at these specific indexes. So if I will try to put I over here and j over here, you can see I is less than j and ai is going to be like greater than aj. Note that the term I am going to talk about is strictly greater because this is important in case of inversion. So here I and here j also, and here I and here j also. So this is like inversion. So if you are talking about a specific term like inversion, you need to just find out two indices I and j so that ai has the value strictly greater than the value present at aj, that is the jth index. Okay, now let's talk about this problem, right? We have a binary array consisting of only 0 and 1. So it will be very much easy to interpret this problem and understand. So we will have like 3 4 cases first. And what is that case? Okay, so we will have the array consisting of 0 1 0 0 0 and all that. Okay, so I'm just writing it down for any two adjacent element. Any two adjacent element. Okay, so let us do that. Any two adjacent element. Now you just focus upon for any two adjacent element. Either I am switching from 0 to 1, or I am, that is, this is the first case, or I am switching from 1 to 0, or I am switching from that is, I'm not switching from 0 to 0, or it will be of type 1 to 1. I'm just noticing, writing down these all one because this is going to be important. Okay, so consider the array of this type, like from for first type, you can see, suppose we have some sequence of zeros, then followed by sequence of ones. Okay, you can see that this term, that is, I'm switching from 0 to 1. Now you can see the array is in sorted form. As I've already said, if the array is sorted form, there will be no inversions. Okay, so whenever you will encounter the type of 0 1, that is when you're switching from 0 to 1, still the inversion there will be like our subarray or our array will be inversion free. Okay, now let's talk about this 0 0 case. Now you can see for this one also, if I will encounter this 0 0, inversion is not going to be increased. If I will encounter for 0 0, inversion will not increase. Now if I will encounter this 1 1, still the inversion is not going to be increased. Still the inversion is not going to be increased. Now the comes the important one, 1 0. Okay, so when I try to just introduce another 0 over here, you can see that inversion is now going to be increased, like because we have some I over here and we have some j over here. I is less than g, and a of I is going to be like greater than a of g. You can see that a of I is 1 and a of j is 0, so inversion is like increased by 1 over here. Okay, so it means that we can just move further till over this position. We can just pick up the subarray from this position, because after that inversion is going to be increased and my array will not be, no, that is my array will no more be inversion free. Okay, so this array as inversion count, inv count, as 0. Okay, so it means that whenever you encounter the adjacent element of this type, you need to just switch over to the next array. Okay, so this is the subarray, right? Okay, so moving further to the code, because it is like no more interesting problem. You can see that first I have taken the input, then my answer will always be 1, and I will start iterating for all the adjacent elements. And it means that whenever I will encounter the array of type, you can see that it is vi is 0 and v of I minus 1 is 1. It means that the value of this type. Okay, so whenever I will encounter a adjacent element of this type, I will just say that I will only pick up this subarray, because this subarray is inversion free and my new array would be starting from this position. Okay, so suppose I am just facing out this one, then again I am facing out this 1 0. It means that again I am just picking it up this one. So it means that I have to move further to do one operation more, and we need to find the minimum operations, right? So whenever I will encounter 1 0, my number of operation will be incremented by 1. So this is the all you have to do, and finally print the answer. The problem is like very much easy. I don't know why the number of submissions is quite very less. Okay, so if you have any doubts, do let me know in the comment section of the video, and let's move further to understand the next problem. Okay, so let's talk about super jump in a grid problem. Okay, so we will be given an n into m grid where every cell is consisting of either 0 or 1. It means that we will be given a matrix where every cell is either holding the value as 0 or 1. A particular cell is blocked if it is holding the value as 1. And if standing at a particular cell, we can do either of these two operations. And what is that operation? We need to understand that right now. We can move right to the very next cell which is not blocked, and we can also move down to the very next cell which is not blocked. If you're not understanding this statement, no need to worry about. Let us understand this right now. You can see that if we are at a particular cell, this one, and we can move from this to this, that is the next unblocked cell. Okay, and suppose if you are at this one, the next unblocked cell is like this is blocked, so we cannot move, and this is also blocked, so we cannot move. So we cannot move to the right. And suppose if here it is not 0 and here it is 1, what is the that how we can move from this cell? You can see we can move from this cell to this cell, right? So this is the basically explanation, and similarly we can move to the down also. And we are initially located at cell 1 comma 1, and we need to determine the number of ways we can reach to the end cell, that is n comma n. And since the answer can be large, we need to consider this modulo operation, right? So let's without wasting our time, let's discuss this problem. So suppose you can see easily that if we are at starting at this position, you need to ensure that source cell and the destination cell should not be like holding the value of 1. If it is, then we have to print 0 in this case. Now you can see the number of ways we can move from this, that is the source cell will be holding the value as 1. Note that I'm talking about the answer, and the problem or the approach that I'm going to use would be dynamic programming, because such type of problems require DP approach. We need to just process the previous values, prerequisite values, to find out the answer for the current state. So we can move from this cell to the next cell, and the number of ways will be same 1, and again the number of ways will be same 1, because because the next unblocked cell we are going to move, and again the number of ways would be 1, number of ways would be 1. Now you can see that if we are at this cell, and that is we need to, now I'm trying to find out the values for this cell. Now you can see it is blocked, so number of values will be 0. Again this will be 0 because this is blocked. Now comes the very important thing. We need to find the value for this cell. Now you can see that for this cell it is unblocked, so we can either come from this cell to this cell. That is, if we are at this cell, the next unblocked cell to the down of it would be like this one. So we can jump from this 0, 1 cell to like 3, 1 cell, and that is we can come from this one to this one, or we can also come from this one to this one. Okay, so what is the answer for my current cell? My answer for the current cell would be like 1 plus this one, so answer would be 2. Now if we are talking about this cell, what is the number of ways to reach to this cell? Number of ways which to reach to this cell would be either we can come from this to this, or we can come from this to this. So my answer would be like 2 plus 1, 3. Okay, so if you can just cross check it out, it is coming exactly 3. Okay, so how we are going to do that? You can easily see one thing that I should have to, I need to maintain the DP matrix of answers, and I need to maintain two more matrices, DP1 and DP2. DP1 is going to store the values for the current cell when we are coming from the up side, and DP2 is going to store the values when we are coming from the left hand side. That is, this cell is going to store if DP1, the value at the value of DP1 for this current cell would be like 1, and again for this DP2 would be also 1 because I need to come from the left and the value is same as 1. Okay, now let's move further to the coding part to understand this in a very simpler manner, because this problem is actually very much easy problem. Okay, so let's first zoom it out. Okay, you can see first I have taken the input matrices. Okay, and it would be a character matrix, and if my source cell and end cell is blocked, just print 0 and move further. And this DP is going to store the answer for a particular cell if we try to reach from 0, 0, that is from source cell 0, 0 to the current cell I, j, let's say, and this dp1 is going to store for the value when we are coming from the up cell, and this is from the left cell. Now you can see this entire two for loops is going to store the, that is it is used for initializing the base case, right, and it is for like initializing the values for this particular 0th row and this particular 0th column. Okay, and I'm doing this for the base values. Okay, you can see if the particular cell is blocked, just continue, otherwise fill the default values as 1. You note that the source cell is not blocked, that is 0, 0. Now I need to just process the values for the other cells. You can see if a particular cell is blocked, dp1 that is coming from the up cell will be exactly equal to the previous value that is coming from the, that is dp1 of ij will be exactly the same as dp1 of I of j minus 1. Okay, so if we need to find out the value for this state, you can see I am coming from this one to this one, and if it is blocked, dp1 will store the exact same value. So when we try to fetch the answer for this cell, I will just fetch the answer for this cell right now. Okay, and similarly this dp2 is for the left one. Now if the particular cell is not blocked, what is the value for dp of ij? We can come from up or we can come from the left, and note that dp1 and dp2 will also be changed and it will be assigned the value of dp of ij, and finally print the answer. Let's submit this code and check it out if this is working fine or not. Yes, you can see all the test cases have passed. So if you have any doubts, do let me know in the comment section of the video, and I will ask the viewers to like this video, share this video, and do subscribe to our YouTube channel for latest updates. Thank you for watching this video.